All right, good morning, everybody. So today we'll continue our discussion about Taylor series expansion. But I guess last time we were halfway through section 9.8. So if you have questions, just let me know in the chat. Let's see. So we did some examples involving deriving the Taylor series expansion for certain functions. So recall that this is the form that we have. So if your center of expansion is x equals a, then the formula looks like this. You have x minus a to the power k. That's a mainstay in your formula. Now there's a k factorial in the denominator, and the most crucial part in this formula is deriving f upper k evaluated at a. Remember that this guy should always be a constant, so there would be no x's coming out of this guy. So the x's are only seen here, okay? Now what you need to do here is to find a general formula for the k derivative and then plug in the number a. So this will be a nice constant for most functions, so you'll get a pattern. And then, yeah, when a equals 0, which is a very convenient expansion, because if this is 0, so we only see x to the powers k. And another nice thing is that most likely, if you plug in a equals 0 here, you will get a nicer or an easier calculation, right? So that's why most people prefer the center of expansion to be x equals a. They love it so much that it's given another name, a special name. It's a Maclaurin series expansion. And here are some common series expansions. Expansion for e to the x, ln of 1 plus x, but I guess this one was derived using the derivative of or the integral of a geometric series. And then you have expansions for cosines and sines. And let me see what we did. What did we do last time? Okay, we started with this example, then expanded 1 over x squared. Okay. And okay, I think that's what we did last time. So perhaps today I'll start with another quick example of finding the Taylor series expansion or the Maclaurin series expansion for some nice functions. In particular, let's try hyperbolic cosine of x. I don't know, is it right that you were not given the formula for the expansion of cos x in the lecture? Because if not, then it's nice to know how to derive the series expansion for cos x. Okay, now that's good. Let's play about let's play with hyperbolic cosine of x. Now again, recall that the function f can be expanded as a series of its kth derivatives evaluated. Let's say this is around, did I put, okay, yeah, around x equals 0. Because hyperbolic cosines and sines are easy to evaluate at x equals 0. So your formula will look like this, x to the power k. K going from 0 until positive infinity. Let me see Kevin's question. Okay, that's fine. I'm going to go to that question after this one, Kevin. Don't worry. Okay. Now, again, there's nothing fancy about x to the power k. You just copy it over, as well as k factorial. Just copy it over in the final answer. The work here should be on finding a formula or how does f to the power k looks like. So for that, we need to evaluate some pure derivatives. Let's start with k equals 0 and see if we can deduce a pattern. When k equals 0, we're looking for f upper 0 of x, but this is simply the function itself. So that's hyperbolic cosine x. And then remember, we need to plug in the center of expansion. So we need f upper 0 evaluated at 0, because that's what the formula calls for. So this would be cos of 0, but cos of 0 is equal to 1. I hope you remember the definition from Cal 1. If not, just go back and see that Cosh is just the sum of two exponentials, e to the x plus e to the minus x all over 2. That's why it's going to be 1. And then let's do k equals 1. That's f upper 1. But f upper 1 is just another way of saying f prime of x. So we need to differentiate cosh. The derivative of cosh is sinh. And then we need to plug in 0 to f upper 1. So this will become sinh of 0. Sinh of 0 is equal to 0. Because sinh is e to the x minus e to the minus x all over 2. So this would be e to the 0 minus e to the 0 over 2. So this guy would be 0. If it was a cosh, it's plus, so it's going to be 2 over 2. That's why I got 1 in there, right? I can't help myself but to explain all the details. So, all right, so that's it. Let's see. Let's try another one. And I guess after this, we can see the pattern. F upper 2 of x is just another way of writing f double prime of x. So we need to differentiate sinh. The derivative of sinh is cosh. Okay. But remember, we need to plug in 0. So we need cosh of 0, which is 1. But notice that here, we're back to where we started. And if I'll do the same thing for k equals 3, I'll see that I'll just have a sinh again. And sinh of 0 is 0. After the sinh, I'll be getting a cosh, will give me a value equal to 1. So it appears that this will just be 0, followed by 1, followed by 0, followed by 1. We have a 1 whenever k is even, right? 0, 2, 4, and so on. And it's going to be 0 for odd number or for odd values of k. All right. So therefore, I can write our f of x, which is a hyperbolic cosine of x, as when k is 0, it's k is 0 is even. So I'll have 1 over 0 factorial x to the 0 plus 0 over 1 factorial x to the 1, because f upper 1 evaluated at 0 turns out to be 0. And again, our marker is the exponent. If the exponent is even, we get a 1. When the exponent is odd, we get a 0. So this would be plus 1 over 2 factorial x squared plus 0 over 3 factorial x cubed plus 1 over 4 factorial x to the 4, and so on. The pattern holds true, right? Now, if you want to have a summation form for this guy, so we still get the summation from k going from 0 to infinity. But again, notice that we get a 1 only for even powers. And all the odd powers will just vanish because they will have a multiplier 0. Okay? So that means I only have even powers of x. So I should write it as a 2k, right? So when k is 0, I'll have x to the 0. Oh, there we go. If k is equal to 1, I'll have x squared. There we go. If k is equal to 2, we'll get x to the 4th, which is this guy. All right. And what's the pattern? It seems that whatever the exponent is, that will also be the number inside the factorial in the denominator. So if I have 2k in the exponent, so in the denominator, I should have a 2k factorial. All right. And therefore, this is our series expansion for the hyperbolic cosine. So now I guess I can add this to our list. So let me just do that. I hope I have space here. I used up all the space, but let me paste that here. Make this guy a bit smaller. Okay. And this is our expansion for hyperbolic cosine. And look at this, compare it with the with cosine. They're very similar to each other, except that the expansion for cosine has negative 1 to the power k. But this guy doesn't have a negative 1 to the power k. So, and that's their only difference. So that's why I think naming this guy as hyperbolic cosine is very apt because it's very similar to cos or to cosine, not only in terms of its derivatives and identities, but as well as for the series expansion. Well, I don't know if hyperbolic cosine will appear in the test, because if you are not taught what the series expansion for for the hyperbolic sine and hyperbolic sine cosine in the lecture, then it should not appear in the in the test, except if you will be asked to derive the series expansion for cosh and sinh. But we already did the expansion, so yeah, I don't think the expansion would be that hard. But if I will be writing the test and I did not show you hyperbolic cosine in the lecture, then I'll ask you to derive the series expansion for hyperbolic sine. So I expect you to you guys to be able to write something like this. But that's just me. I don't know what will happen in your exam. But it's nice to know more than less. So yeah. You can remember the expansion for hyperbolic cosine by just imagining the expansion for cosine without the alternating sign. And another thing is that this proves that the hyperbolic cosine is an even function because it only involves even exponents in the expansion. Similarly, the series expansion for hyperbolic sine is just involving the odd exponents. Okay. Because you see, you would have started with k equals 0 here. This would be your k equals 1. And the same pattern goes on. So you'll have 0, 1, 0, 1, 0, 1. So the rows will just be interchanged here. So only the odd powers will remain. So this would be our expansion for hyperbolic sine effects. And then let me just copy this all over the top. So here you'll have at the start of the worksheet, the list of some common series expansions. All right. Any questions for that? I hope that the thing is clear. And again, the crucial part here is evaluating the derivatives and plugging in the center of expansion. Right. So if there are no questions, I'll proceed to problem 4, which is the one Kevin sent. Let me just see what my instruction here is. Find the series expansion. Okay, let's make an exception for problem 4. Let's use this instruction. Say find I'll answer a very similar one to your to this question, Kevin. I'll just use a lower degree polynomial so that I don't have to write many terms. So here I'll have, let's say, just the 6th degree Taylor polynomial. Centered at x equals 0 for the following function. For, let's say we have a specific function here. Let's say we have x cubed cosine 4x. Let me just make it 5x just to make it different a little bit. Then find f upper 5 at 0. let me see. You will use f upper 5, or you'll use this answer to get f upper 5 at 0. Though that should be... I don't know what they... okay, I see. I see what they want to do here. All right. So yeah, our function here is this guy, x cubed cosine. Maybe I should not start there. Right? So this is our function that we want to get the 6th-degree Taylor polynomial for. And then aside from that, we need to find the 5th derivative of 0. Without the knowledge of the, without knowing the expansion for f, then finding the 5th derivative will be very tedious because you'll need to find the 5th derivative, and imagine how difficult it would be, because here you have a product, you need to use the product rule, and so taking higher degree polynomials will get messy and messy. But we can take advantage of the series expansions here. All right. Now, this guy x to the power 3 doesn't need any expansion because you can keep it as ease. We'll take advantage of the expansion for cosine 5x. So for this guy, let's see. Let's recall that cosine of x has the following expansion. It's the sum, k going from 0 to positive infinity, of negative 1 to the power k of x to the power 2k over 2k factorial. Okay, so that's the expansion for cosine x. But we have a cosine 5x in our function f. So, but that's easy because we already know the base formula for the expansion of cosine. All I need to do to get an expansion for cosine 5x is to replace all x's I see here by 5x. So here, I'll copy the summation, except for the x's. I have an x here. I'll replace it by 5x. So that guy will be raised to the 2k all over 2k factorial. K going from 0 to positive infinity, right? So this is how you take advantage of known series expansions. That's why you will save a lot of time if you can remember those series expansions, right? So because here I don't need to derive anything for cosine 5x. I'll just need to use the formula for cosine, replace all x's by 5x. All right. So I'll take advantage of these, and now we know that f of x will be what? This is x cubed times cosine 5x. Now I'll copy x cubed over. But this time, I'll replace cosine 5x by its expansion. Okay, so that's the expansion of cosine 5x. And then I can use the distributive property of multiplication over addition to put x cubed inside of the sum. But probably before I do that, let me simplify the sum first. Play with the loss of exponents. I still have a 2k factorial in the bottom. I'll have a negative 1 to the power k. Now this is 5 times x raised to the 2k. So I'll split them up into a product of powers. So loss of exponent tells me this would be 5 to the power 2k times x to the power 2k, right? But this guy can be further simplified. Okay. Now I have 5 to the power 2k. I can look at it as 5 squared raised to the k. So I can write it as 25 to the power k. Just to make it look simpler, right? But you can leave it as 5 to the 2k. That's fine. Then I guess now I'm ready to put x cubed inside the summation. So I'll have the sum of negative 1 to the power k, 25 to the k, x to the 2k plus 3, because remember Remember, when you're multiplying powers of the same base, you simply add exponents all over to k factorial. K going from 0 until positive infinity. And I guess here, I wanted to make it interesting, and I see now why they want the 9th degree polynomial. So let's give it back to 9 just to make it more interesting, because I don't need to write a lot of terms. But yeah, I just need a degree, the Taylor polynomial of degree 9. So this is how f looks like. But if you want a Taylor polynomial, which will be a nice approximation to your function f, we are doing P9 of x. So we need to get the degree 9 polynomial from the Taylor series expansion. So that means we need to plug in values for k starting from 0 until to that k value that will make this x to the power 9. And hence to get a polynomial of degree 9. So let's start at 0. Plug in 0 for all k's you see here. So we get 25. This would be -1 to the 0. That's 1. This guy would be 25 to the 0, that's 1. This would be 0 factorial, that's 1. Then if k is 0, this would be x to the power 3, right? So that's what happens when k is equal to 0. Is that good? Or do you want me to show the details there? But again, this is found by just substituting k equals 0 into this guys. And most of them can be simplified mentally. Is that good? All right. We cannot stop here because all we have so far is a polynomial of degree 3. Let's do the next term. Next term is k equals 1. So k equals 1. Oh, this would be negative. This would be 1, -1 to the first power. So we have a negative sign there. Then we get 25 to the 1. And then what do we get when k equals 1? We get x to the 5th all over. K equals 1, so this would be 2 factorial, but 2 factorial is just 2. Okay. And then we cannot stop here. This is just the 5th. This is just the 5th a degree 5 polynomial. So let's move on to k equals 2. When k equals 2, this would be -1 squared, which is 1. Then we'll have 25 squared. That's a big number, so I'll keep it as 25 squared. When k is 2, this guy will be x to the power 7. Is that right? K equals 2, yeah, x to the power 7 all over 4 factorial. Right? But 4 factorial is what? Well, 4 factorial is 4 times 3 times 2. So that's going to be 624. So I'll replace it by 24. We can't stop here because here we have degree 7. So let's go degree 8. Sorry, we'll go to the next k value, which is k equals 3. K equals 3 will give us -1 to the power 3. So that's a negative sign there. We have 25 cubed. And then x to the power when k is 3. When k is 3, we get 9. Oh, there we go. We'll stop here. And then we'll have 6 factorial, right? So this would be 2 times 3, 6 factorial, I guess, is 720. Is that correct? 5 factorial is 120, so times 6, so 720. Okay, there you go. This is your polynomial of degree, the Taylor polynomial of degree 9. All right. Okay, and then let's follow up. Let's do the follow-up question. The follow-up question is, what is f upper 0 or f upper 5 evaluated at 0 all over Oh, sorry. Yeah, just that. F upper 5 to the upper 0. And if you look at this formula we have here, F upper 5 will be obtained. Remember in the series expansion, this guy is equal to F upper K at 0 all over K factorial times X to the upper K. Maybe I'll just verbalize that here. Recall that f of x is the sum of f upper k evaluated at 0 over k factorial x minus x to the k going from 0 to infinity, right? So this is the general formula for any Taylor series expansion, right? So what do we notice here? Oh, I'm looking for f upper 5 of 0, right? But f upper 5, 0 is related to the coefficient of x to the 5th, right? So that means the coefficient of x to the 5th is equal to this guy. This would be the coefficient of x to the 5th, right? Again, I surmise that because if I look at this formula, I will get an f upper 5 if I have x to the 5th. So if I know the expansion of f, all I need to look at is the coefficient of x to the 5th, and whatever is beside x to the 5th, that would be my f upper k or f upper 5 evaluated at 0 all over k factorial. Does that make sense? Yeah, I'm being very verbose here, but hopefully that made sense. Again, this is the general formula for any series expansion. You're looking for f upper 5, so you'll get an f upper 5 from the coefficient of x to the 5th. So if you know the expansion of f, just look at the coefficient of x to the 5th. The coefficient of x to the 5th will be this guy, right? That should be 5 factorial, right? Now, if we look at our expansion for f, oh, this is an abridged version of our expansion for f, right? There would be several more terms here if we're looking for the exact f. But remember, we are interested in the coefficient of x to the 5th. What's the coefficient of x to the 5th here? The coefficient of x to the 5th is this guy. And according to our formula, negative 25 over 2 will be equal to f upper 5 evaluated at 0 over 5 factorial. Because according to the formula for Taylor series, whatever beside is x to the 5th is equal to f upper 5 evaluated at 0 over 5 factorial. So yeah, that's right, Kevin. So f upper 5 evaluated at 0 over 5 factorial equals negative 25 over 2. And since we're looking for f upper 5 evaluated at 0, I simply need to multiply this guy by 5 factorial. If you want to simplify, 5 factorial is just 120 over 2. So this would be 60 times negative 25, whatever this number is. Hold on. What is this number? So 30, 12, 1500? Okay, great. Does that make sense? Okay, great. Okay, yeah, sure, Christina. Though for this one, Yeah, probably I'll write the solution here to our previous worksheet, worksheet 19. I'll just update it later. Let's try number 9. I think we also did a very similar one to this. Let me see. Yeah, I just changed the constants. But anyway, yeah, let's try this one. I'll vary the constants once again. Let's try. Say let's have 1 over yeah, let's try 1 over 10 plus x as a power series. There's several ways on how to do it. Should I do it via powers of I'm thinking to do it via powers of yeah, I'll stick to powers of x because I can do this as powers of x minus 21 or 21 minus x, but I'll keep it simpler. I'll first rewrite it as oh, it's 10. I was looking at 1 over 20 plus x, but I look at it as this. I'll try to factor 10 out first. So I'll have a 1 plus x over 10. Okay. Because I am banking on using the geometric series expansion. So recall the sum of a over 1 minus r is equal to the sum of ar to the k going from 0 to infinity. This is what I'm trying to use. And this requires to have a 1 in the denominator or start the denominator with a 1 minus. So there was a 10 here, so I want to make it a 1. One easy way is to factor a 10 out. So you have a 1 ready here, but we still have to remedy the negative sign here or the positive sign here. It should be a minus. So I'll manipulate the given expression more. Instead of the 10, I'll put the 10 in the denominator for the numerator. I can write it as 1 over 10 times 1. The form requires a minus right after the 1, so I'll need to comply with that. And then to remain equal to this guy, I have to have a minus negative x over 10. Okay. Now, I hope it's clear that this guy is equal to this. And why I did that manipulation or rewriting. Again, because I want to use the geometric series for this. Okay, good so far? Christina said this might be in the free response, so I want to get your feedback. Is that good, Christina? Okay. Now, again, the reason why I want to do this is so that I can compare this guy with this guy. And clearly, A is the one in the numerator, so A is equal to 1/10. And R would be the one right after the minus sign in the denominator. So I have a 1 minus, oh, this must be my R. R is negative x over 10. The negative sign included. So don't forget about that, right? So now I know that g of x being 1 over 10 plus x is the sum of, again, we have rewritten this guy in this form and found out that A is equal to 1/10. So we'll have a 1/10 there. And then R, we found out to be negative x over 10 raised to the power k k going from 0 till infinity. Okay. Now let me play a bit with the loss of exponents here to make the expression easier to look at. So I'll have a 1/10 outside. Loss of exponents here, I have a -1 raised to the power k. I'll just isolate it here. Then I have x to the power k that goes on top. And then the 10 in the denominator is also raised to the power k. So I'll have this. K going from 0 till infinity. And then this will become this. I'll copy the -1 to the power k, x to the power k on top. But in the denominator, I have a 10 here. I have 10 to the power k. Multiply them together, we'll get 10 to the power k plus 1. So this is your expansion for 1 over 10 plus x. All right. Now there's a follow-up question. It says to express f of x equals ln of 10 plus x as a power series using the answer in problem 9. Okay, so again from 9, this is what we got. 1 over 10 plus x is equal to this series. Okay. Now, in order to be able to use this series expansion, I want to see what is the relation between one over 10 plus x and ln of 10 plus x. Because once I know the relationship between them, I can engineer this series into a series that is apt for ln of 10 plus x. All right. Now you have a rational function, you have an ln, so this screams integration. All right. So recall that when we integrate 1 over 10 plus x dx, we can let u to be equal to 10 plus x, du will be dx, right? So this guy will be integral of u over, integral of du over u, which is ln of the absolute value of u plus the arbitrary constant c. Okay. And this would be ln of the absolute value of 10 plus x plus the arbitrary constant c. But remember, hold on, here, this is true only whenever the absolute value of -x over 10 is less than 1. Remember, geometric series only converge when the common ratio has absolute value less than 1. So this is true only when absolute value of x minus 10 or -x over 10 is less than 1. Okay, but what happens when this is true? When the absolute value of x over 10 is less than 1, then this guy will become positive. So we can say for x's with -x over 10 less than 1, or equivalently, this is what? Absolute value of x is less than 10, then this guy is always positive because our x's has magnitude less than 10. So we'll have ln of 10 plus x is equal to the integral of 1 over 10 plus x dx. Okay, and the arbitrary constant c is hidden right inside the integral there. Okay, is that clear before we move on to the next step? All right. Now let's take advantage of our answer from problem 9. From problem 9, we already found a series expansion for this guy. So I can replace 1 over 10 plus x by its series expansion. So I'll copy this. So this guy will be inside the integral, everything multiplied by dx. All right. So what happened? I just replaced 1 over 10 plus x by its series representation. Okay. But what's the beauty of doing that? Well, for x's in the interval of convergence, the series is absolutely convergent. And when your series is absolutely convergent, you can interchange the integration and the summation. So instead of integrating a series, we can instead take the sum of integrals. But be careful with this because you can only do this for absolutely convergent series. And luckily for us, everything in Cal 2 is assumed to be absolutely convergent power series. So we can always interchange the summation and the integrals. But when you go to higher math courses, you need to check if the given series that you're dealing with is absolutely convergent. All right. Okay, now we simply need to integrate this, and they will reside inside the summation. But take note that here we are integrating with respect to x. So everything without an x will go out of the integral. So this doesn't have an x, as well as the denominator. So this guy doesn't have an x. So you can take them out of the integral sign. So we'll only have e to the power x dx left in the integral. And that's not hard to evaluate. Because here it's just x raised to a constant. You can use the power rule. So we'll have negative 1 to the power k over 10 to the power k plus 1 times x to the k plus 1 all over k plus 1. Because basically this is the integral of when you integrate this guy, you get this plus some arbitrary constant c. Okay, and this is our guess, or this is our series expression for ln of 1 plus, 10 plus x. Okay. Now what's left to be done is to find the arbitrary value of the value of c, because we want this guy to be equal to this series, which comes with an arbitrary value for c. So to find the exact value of c, maybe we can plug in 0. The nice thing is that when we plug in 0 for x's, this will become 0. So everything in the summation will become 0, leaving us only with the value of c. So what I'm trying to say is that when x is equal to 0, then we'll have ln of 10. That's what we get by plugging in x equals 0. So we get ln 10 equals the sum of negative 1 to the power k, 0 to the k plus 1 over k plus 1 times 10 to the k plus 1, k going from 0 to infinity, plus c. But again, I mentioned that here you're just summing up exact zeros, right? So the sum of zeros will just be 0 plus c. So that means c is equal to ln of 10. So that finishes up our solution, telling us that that the ln of 10 plus x is equal to the series plus c, and c happens to be ln of 10, right? Because here c is equal to, let's raise it, oh, there we go, equal to ln 10. So that's why I got that value of c. Yeah, so yeah, you're right, Christina. Sometimes the way problems are phrased are very intimidating. So you guys might skip the problem and pray that the next one would be easier. And the worst case is that you come to the end of the test and you're still praying. So the thing is, try to read the problem carefully and try to dissect it or to break it down into smaller pieces. Because once you start doing the work, then hopefully things will become clearer and you will see the next step after you did the first one, right? And again, if you are asked to find, probably this is my tip, if you're asked to find a series expansion for a certain expression, try if you can write it as a geometric, to be geometric in form. So try to write it as a over 1 minus r, or something that comes out of a over 1 minus r, like the derivative of a over 1 minus r, or the integral of a over 1 minus r. Okay. Otherwise, you need to go to Taylor series expansions, which is much more tedious than previous expressions. All right. Okay, I hope this makes sense, and hopefully you get it, and something like this will appear in the exam, so you will be guaranteed um, some points for at least one FRQ question. Let me see. We still have 3 minutes left. Well, what can I answer in that time? Perhaps you have questions? Maybe let's go to series expansions. We already did 1 over 1 plus x squared. Oh, monotonicity. Well, there are several ways on how to do monotonicity. I'm not sure if you guys, if I ask you guys to ask Dr. Almas if she allows just observing the degree of the top in the denominator for testing for monotonicity, or was it my other class that I asked, that I told to ask? Yeah, because that will make your lives easier for most functions. Because for instance, how to check monotonicity? There are several ways. For monotonicity, you need to say whether it's increasing or decreasing all the way, right? So the question here is it decreasing or increasing for all terms, right? So one way to check it would be to see if an plus 1 minus an compared it to 0. So if this is, so you compare it with 0. So we're not sure which is less than or greater than. If an plus 1 minus an is less than 0, that means an plus 1 is less than an. So that means an is larger, so you have a decreasing sequence, or you have a decreasing term. If you have a reverse inequality here, then you say it's increasing. So you just need to take a look at a sub n plus 1, subtract from it a sub n, and observe the sign. But sometimes doing this is not easy, or it's not apparent if it's less than 0 or greater than 0. So you need to do a lot of algebraic manipulations. Another trick that you can use is, if that is hard, you can try a sub n plus 1 all over a sub n and compare it with 1. Because if you found out that a sub n plus 1 over an is greater than 1, then that translates to an plus 1 greater than an for positive ans. I need to put that caveat here because when an is positive, multiplying both sides by an doesn't change the inequality, right? So that means if you were able to show this, then you can conclude that the sequence is increasing. And if it is true for all n's, then that means it is monotonic increasing, right? This is my favorite way because usually this is also hard. especially if you have terms like n plus 1, if you have n to the 5th plus n to the 7 all over n to the 8th plus n to the 6th. Imagine how a sub n plus 1 looks like. Oops. A sub n plus 1 will look like n plus 1 to the 5th plus n plus 1 to the 7th all over n plus 1 to the 8th plus n plus 1 to the 6th. And if you do the subtraction or you do the division for either of these two bullets, then this it's hard to simplify this and see if it's positive or if it's greater than or less than 1. So it's quite difficult. So my favorite way to check monotonicity is to define your function f of x so that f of n is equal to an. So basically in this step, you just replace all x's, all n's by x's and look at f prime of x. If this is negative or positive. Because remember, if the derivative is negative, then f is decreasing from cal 1. And if f is decreasing, it follows that an is also decreasing. So if a sub n, if checking the difference or the ratio is hard to do, then you can take the derivative. And most of the times I find it easier to find the derivative and observe whether it is positive or negative to conclude that it is monotonic increasing or monotonic decreasing. All right. But for the AST, it's much simpler because if Professor Almos will allow you to argue it this way, you can say that for my previous example, I have this. For instance, you can try any of these 3 bullets here to show that this is decreasing, because remember for the AST, you need to show that AN is decreasing. Right? If this is your AN, any of the 3 bullets I listed is difficult to perform. All right? Now, but you can argue if it will be allowed, because it depends on how you stated the alternating series test in the lecture, right? You can argue that the numerator is degree 7, the denominator is degree 8. So that means the denominator grows faster than the numerator. So when the denominator grows faster, that means that this is eventually decreasing. Because in the long run, the increase in the denominator will outpace the increase in the numerator, making the fraction eventually decreasing in value. All right. So that's why I say, okay, this is eventually decreasing. Which one do you mean to be divergent, Kevin? Are you talking about the sum of this guy or the sequence? Oh, the sum. So it should be an alternating sum. If there's an alternating sign, then the AST will tell us this will converge. Why? Because if you look at the positive term, it will be eventually decreasing. The limit of the positive term is 0 because the denominator goes to 0. And those are the 2 requirements of the AST. Both conditions are met, so the alternating series is convergent. Now, if you're talking about the one without the alternating sign, this is also convergent because you can do LCT, limit comparison test, with the series that behaves in a similar fashion. Now, the numerator in the long run will behave like n to the 7th because n to the 5th will become eventually insignificant compared to the n to the 7th. in the denominator, the driving force is n to the 10th, the highest power. So this guy will simplify to 1 over n cubed, a p series with p equals 3, which is convergent. So if you do the limit of this guy over the testing series, 1 over n cubed, as n approaches infinity, this will be, by design, this will be n to the 8 plus n to the 10th all over n to the 8 plus n to the 10th as n approaches infinity. This will just become 1, right? And this is a finite constant. Remember the LCT. If you take the limit of the ratio of the terms in two series and it happens to be a finite constant, not equal to 0, then they will either both converge or diverge. But my testing series is 1 over n cubed, which is a convergent p series because p is equal to 3. So this converges. So this guy will also converge because they behave in the same way in the limit. I hope that helped, Kevin. Yeah, whenever you have an algebraic over an algebraic expression, limit comparison test is much simpler because you'll just need to ignore lower order terms in the top and in the bottom. Then that will simplify into a nice p series, which you already know to be convergent or divergent by just looking at the exponent. And once you do the limit by design, you should get a non-zero finite constant. And so you will have a conclusion either way, whether your given series is convergent or not. And to complete the review, your alternating series is convergent. The series without the alternating sign is also convergent. So this guy is absolutely convergent. Because on its own, it is convergent. And with the absolute value, meaning you remove the alternating sign, it is still convergent, then it is absolutely convergent. All right. Okay, so I think it's a good time to stop here. Have a good weekend, everyone, and let's see each other back on Monday. Bye, guys. Oh, probably on Monday we'll continue our review, so it will be great if you'll come in with your questions, all right? Okay, bye, guys.